Now I
Well,
see
good
on
afternoon,
air.
everybody. There we go.
Mm-hmm.
We are live. So good afternoon, everybody. This is Brian Benish with DSIAC. Thanks for joining us this afternoon for this webinar. I'm going to give a quick introduction to DSIAC as an organization, just so everyone kind of is familiar of who we are, what we do, why we're offering this presentation, and then I will give the over to Dr. Wu to deliver his presentation. At the end, we'll do a little bit of Q&A, and I will guide you through that. I'll show you what that looks like in just a moment. But again, as an introduction to us as an organization, DSI, we're the Defense Systems Information Analysis Center. We are a DoD entity that is organizationally under DTIC, the Defense Technical Information Center, DTIC. DTIC, I like to describe them as the DoD's digital library. Any and all technical publications that was produced at least in part by DoD government funding should be in the DTIC's library. They've probably got 4 million plus records in there right now, a wealth of information, and so DTIC has recognized, the DoD community has recognized that there's a lot of information out there that makes it difficult to navigate. And so what they've done is they've stood up these IACs, Information Analysis Centers. So we're one of 3 of those under DTIC that are in existence right now. We operate the DS IAC, the Defense Systems IAC. There's also an HD IAC and a CS IAC. And what we do is we're set up to help folks who are performing defense-related research and engineering efforts to help them find the information that they need. And so if you're conducting some sort of research effort, we're here to help find information, help make sure that you're not repeating work that's been done before, collaborate maybe with other folks who are doing similar work, and maybe stimulate some sort of innovation. And so a chief way that we do that is through our technical inquiry service. We are fully funded to conduct about 4 hours of research time on behalf of any technical question that you might have. So, and this is for DoD, government, and contractors. So if there is a technical question you have, or a project you're working on, or a project you're attempting to work on or planning to work on, you can ask us. We have technical folks on staff who are familiar with with many technical details within our technical focus area, our domain of defense systems, which is comprised of autonomous systems and directed energy, survivability, weapon systems, a whole host of topics. We have a lot of technical folks on staff who have expertise in those areas, so they understand your topic and have an understanding of the DoD landscape, industry landscape, academia, those interactions, so we can help identify where we're doing that work and connect you and give you the latest information. So I would encourage you to go to our website, DSIAC.org. If you haven't already done so, poke around, take a look at more information about who we are and what we do. And one way that we help fulfill our mission is by offering these webinars, these technical presentations from folks in the DoD research engineering, create an awareness of work that's being done, and again, ultimately to help mitigate the redundancy and help foster collaboration. So we're happy to have Dr. Wu here to present his webinar. It looks like the webinar's slides have been taken down for a moment. I can quickly. Bring it. When we get to the end, I mentioned question and answers. Oh, and drop. Platform. You should see up towards the top of your screen a little box for audience questions that you can click on. I would encourage you at any time during the presentation to type in a question. That'll kind of get put into a queue, and then when we get to the end, we'll walk through and discuss those questions. I just want to distinguish the questions portion from the chat. There's a chat that you can participate in if you want to chat with the presenter or send a note to other attendees or something like that. You can certainly do that, but I would encourage you, if you want to get a question answered in the Q&A portion, to make sure you hit that audience question button question. Okay, so that's a long administrative kind of introduction there. Without further ado, Dr. Wu, I'd like you to take it from here if you could.
Okay, great. Thank you. Thank you for providing me opportunity to present this webinar presentation. And I'm from Naval Research Lab. Now it's more than 20 years. And before joining NRL, I was a faculty member at the University of Maryland College Park. And also prior to that, I was a member of technical staff of GT Lab, which is now Horizon Laboratory. Anyway, the presentation that I'm going to give today is a 3-axis non-intrusive electro-optic field sensor for electromagnetic test and evaluations. This project was supported by several funding agents. One of them was Test and Resource Management Center at the OSD, and the other is China Lake, and another one was DITRA R&D. And I appreciate all their funding, and the funding enable us to develop much better sensor and a more reliable one. And so I'm going to present one here today. Okay. How do I go next slide? Hello? Hello?
Go ahead. Yep, I can. I'll progress them for you if you want to. If you would like to, you can click on the arrows.
What should I press to go next slide? Click on the mouse. Okay.
Yep. There. Yep.
Okay. Before I present the sensor itself, let me explain the background why we need non-intrusive sensors. The test environment, field test environment, is very complex sometimes because of some metallic and dielectric materials strewn in the field test site, and those obstacles or materials or object distort E field and B field. So unfortunately, this slide cannot be, there's any video, but it cannot show video. Point is, there is small little things pointed by yellow arrow, this one. Once you start to move in the video, it moves. This pattern, electromagnetic wave pattern, changes quite dramatically. Even though its perturbation is small, it changes a lot of different, generate a lot of different patterns. So-called, we call butterfly effect. Okay, so that means the sensor that you measure or measurement system shouldn't disturb or perturb a field by itself. Okay. Next slide. Next slide, please. Okay. Similarly, when we do a field test, the frequency source is not really stable. It jitters back and forth. For example, it changes from 9.3 gigahertz to 9.6 gigahertz. Then this wave path, mode, field mode changes very dramatically, and the variation of that could be 1 or 2 order of magnitude larger than expected from theory. That means those mode change has to be measured experimentally. You can't just do computer simulation. You can't just assume it. Everything is just following theoretical models. So true measurement is very important. Next slide, please. Next slide, please. Okay, one of the tests that we do earlier is actually some other test and evaluation people do. They put sensor inside or some equipment inside reverberation chamber, and there's mode stutter inside the reverberation chamber that constantly rotates and agitate the field, so they can see how the field agitated field affected their device. but they want to know how this field pattern changes with this monster motions. Whenever they try to do that, they get very inconsistent and irreproducible results. Even if they carry out same experiment in the same condition, they couldn't obtain reproducible result with the conventional sensors. So we replaced this conventional sensor with the electro-optic sensors here and there. Then we perform the experiment, we get very reproducible and consistent results. So that is the advantage, one example of advantage of our sensor that can be used for test and evaluation. Next slide, please. Next slide. Next one. Okay, there are several non-intrusive electromagnetic field sensors. One of them is NRL developed electro-optic field sensor. The other is MO sensor. I'm not going to present this. I'm going to present electro-optic field sensor today. But there are other sensors like Mach general interferometric E-field sensor or slab-coupled optical sensors, SCOS, developed by a few different research groups. This Mach general interferometric sensor is already available commercially, and some people try hard to make it field deployable, but we see some problem with it, and so we parametric sensors to some degree, but a lot better than these sensors. And now, why do we need non-intrusive sensors? The main reason, one of the main reasons, is perturbation. If you put conventional field sensor, as soon as you put that in, the external field distorted by the sensors, because these sensors contain either metallic component or semiconductor component, so they distort the field. In addition to that, it contains most of them using coaxial cable to transmit data. So this coaxial cable, as a metallic cable, it distorts the field too. So what you measure is not true field. You measure is a distorted field with conventional sensors. In contrast, if you use non-intrusive sensor like our electro-optic sensors, they all made out of dielectric materials and utilize optical fibers. So they don't disturb field. So field is just straight and it's not distorted, and you measure is true field. Next slide, next please. Next please. So in addition to that, perturbation, lack of perturbation problem, EO sensor, electro-optic sensor, has a lot more other advantages. It is very compact in size, typically less than 1.5 inches old, and one sensor covers all frequencies, meaning 0 frequency to 20 gigahertz. And its frequency response is, for example, here, responsivity is flat. Compared to conventional ones, for example, dipole antenna, it has a huge frequency dependence. So because that means the sensor detects all three components correctly. So if you put wideband signal like this, and the sensor just duplicated the signal exactly. Whereas dipole antenna, some other conventional sensors cannot duplicate the pulse that kind of pulse. And also the sensor has a very large dynamic range, namely from 0.1 volt per meter to 500 kilovolt. And contrasted to that, conventional sensors, this is amplified research sensors. The sensor is limited. The maximum field should be less than 1 kilovolt per meter. If that exceeds, the manufacturer doesn't guarantee the warranty, the avoid warranty. So ours have order of magnitude stronger, larger dynamic range. And because of the optical fiber and the dielectric nature, you can set up experiment quite easily in any way, very straightforward, without any caution, and measurement is just right. So next slide, please. Next.
Hey, Dr. Wu, just as a heads up, there's a bit of a lag between when I click the next slide, so just bear with me. It's coming. I just
yeah, okay, fine. It's fine. So far, it's okay. Great. When we developed the EO sensor, we have to consider a few issues like a thermal effect because field test site, the temperature changes quite dramatically, even in one day. So there is some temperature dependence issue with the sensors. So we have to address all the problems if there is any temperature dependence. And the other thing is, often these sensors are abused. They step on it and they drop it. So mechanical stress has to be taken care of. The sensitivity has to be very large range, over say below 1 volt per meter to say 500 kilovolt per meter, things like that. So you can detect all kind of RF signals, and so you can survive also because of mechanical problems. Humidity and other chemical reactive gases should be taken care of so you can survive in the environment. Next, please. Next, please. So this is basically the sensor structure, EO electro-optic sensor structure that developed by NRL. And before I move on to the sensor itself, let me explain how the underlying physics of the sensor. The key point is this: in the sensor there is EO crystals, and the laser beam is going through the EO crystal. This laser beam is polarized, linearly polarized, angle at 45 degree incoming. So optical field component in X and Y component are equal because this one polarization is 45 degree. So once this optical component, X and Y component, go into the crystal has two different refractive index in X and Y. Because the refractive index is different, the phase velocity of this optical field will be different. So because there are difference between phase, when you combine them, it becomes linearly polarized to elliptical polarization, circular polarization, then elliptical polarization, then eventually linearly polarized. In other words, this linearly polarized beam went through the crystal and the polarization state changes. So once this polarization state changes and it just polarization angle is parallel to the analyzer, maximum field brightness just appears. And if it is orthogonal to analyzer polarization, then it becomes dark. So this is how we detect the polarization. The next slide, please. Next, please. So now that earlier I said refractive index in x direction and y direction are different. So here is how we create a different x and y refractive index. The crystal that we use is KDP crystal, and the crystal when you grow, it looks like naturally comes out like this kind of shape. Then the x-axis of the crystal and y-axis and z-axis are defined that way, and each of them have different diffractive index. If you put it this way and you send probe beam in the direction of that way, then that shows refractive index and extraordinary refractive index, which is smaller than ordinary refractive index. So that's a three-dimensional picture. If you make a two-dimensional xz plane, then refractive index n sub O is larger than refractive index n sub E. So next slide, please. Next, please. Now, if you send the beam, probe beam, in angle, that means you basically tilt the z-axis to z prime. Then, once you tilt it, then refractive index in z prime is smaller than n sub e. And x directions, it becomes large. Actually, n sub e becomes larger, and n sub o in this case becomes smaller. So now, as the refractive index in x prime is smaller than refractive index in y directions. That's how we create different refractive index in x and y directions. Next, please. Now, once you have different refractive index, then you apply E field. Then this E field creates the Pockels effect, so-called electro-optic effect, and changes refractive index of x and y directions. So that's electric field induced refractive index changes in x and y directions. So because refractive index changes, phase velocity also changes. So this polarization direction changes furthermore. So phi sub e, that's the polarization angle changes. And so it has direction change as combination of 0 plus phi sub e. Phi sub 0 is natural polarization because of crystal itself, and phi sub e is polarization rotation due to E field. Now then goes into the polarized beam goes into analyzer, then it causes amplitude modulation. If the E field changes, then polarization changes, swings back and forth, then modulation amplitude is modulated, then photodetector detects it. Now, photodetector detects both phi sub naught, which is natural polarization, and EO effect, phi sub E. So phi sub 0 goes to this component because this one doesn't change, well, in theory it doesn't change, it's constant, about constant, and that is basically RF signal. So we measure two components in this case, with DC component and RF component. Next, please. Next, please. So once polarization changes and goes to analyzer, then this probe beam, laser beam intensity here is depending on the polarization angle of that. Theta 1 is polarization direction of polarizer. Theta p is analyzer polarization direction. So pi is polarization rotation angle here. So it goes like the amplitude, intensity of a laser beam modulated here, following that equations. So if you see that here, transmissivity of a system, TR, and intensity of the beam here, then photodetector responsivity, R sub D, then that is basically produce voltage signal from the photodetectors. That is including DC component and the RF component. So we separate that because we utilize that condition. Theta 1 and theta p is aligned cross polarization alignment. So the angle difference is 90 degrees. So using that, we can separate that, rewrite the equation and make two different terms. One is static term, the other is EO term. That is, static term is actually related to probe beam power, and that EO power is given this way. Okay, next please. Now, EO signal goes like a sine phi E function. So it's nonlinear, but if phi E is small, not very big, for example, here about 300 kilovolt, below 300 kilovolt, it's basically linear, almost linear. So we replace it with a K phi E linear term, then this signal, EO signal, look like this. And these are basically constant and related to material parameters. So basically, voltage EO signal is proportional to E field. Now, conventional method measures this EO signal, and multiply these parameters, and then extract E field strength. The problem is these parameters, PR, and responsivity, are not really truly zero. Especially this probe beam intensity changes over the time. So it gives a lot of uncertainty. For example, if probe beam changes, say 10 millivolt to 20 millivolt, then the EO output increases almost twice as much. So we have to take care of this because none of the lasers are that stable. So next thing that is we consider this thing and solve the problem. Next, please. So in that case, we measure both DC power and the EO signal and measure the ratio between two. M sub EO is VEO over VDC. That means we call this as a modulation depth, EO modulation depth. Then it becomes proportional to E field. Of course, there's a parameter is depending on the dielectric function. We will just ignore that at this moment. We'll explain that later. So E field can be measured by measuring this ratio, MEO, modulation depth, times conversion factor. This conversion factor can be calculated considering these parameters, or you can just by carrying out calibration and find out these conversion factors. Next, please. Next, please. Next, please. Next slide. Next. Okay, so now conversion factor, and from previous equation goes like this. So E field is proportional to EO modulation depth. Now conversion factor, how this behave? Would it be the same for all different frequencies? In one way, it's not. If you measure at low frequency and high frequency, let's say 10 megahertz to 2 gigahertz, it changes. So conversion factor changes. At very low frequency is very high. That means responsivity is bad. As it goes higher frequencies, it becomes low. That means responsivity is very good. Beyond about here to there is a nearly flat frequency response. If you measure that at 1 gigahertz, conversion factor is about 478. But if you use a 5 nanosecond pulse, conversion factor is about more than 9,000. Means the pulse shape is also affecting the conversion factor, and that is because this pulse contains a lot of low frequency component. That's why it has larger conversion factor. Next, please. Next, please. Now, how we compare? When you compare with the DDOT, how they look like. So first, we put DDOT sensor in the TEM cell, 353 volt into the TEM cell. That's a pulse, about 5 nanosecond pulse. Then DDA sensor produces about 1.3 volt. You see the waveform is different because DDA measures time derivative waveform, dE over dt. And so if you integrate it, then you may be able to obtain this pulse, but not actually really, because DDA sensor's bandwidth is limited. So it just changes distorted waveform, even if you integrate this one. In contrast, if we put EO sensor in the same position, it measures exactly the same waveform. That's input signal to the TEM. That's EO sensor signal. As you see, it duplicates the signal, but it produces a little less power, voltage, 44.8 voltage or 8 millivolt, whereas DDA sensor produces about 1.3 volt. DDA sensor is at this sensor. It's about 29 times higher output. But besides that, DDA sensor distort the field, and it cannot detect waveform precisely. I'll come to that next point. Next slide, please. Next slide, please. Okay, so now let's compare DDOT and BDOT, our EO sensors. What if earlier I said if you have sensor that contains metallic piece or or semiconductor in it, it can distort the field. Now let's see how this DDOT sensor distorts the field. Now this DDOT sensor was sitting here inside the TEM cell, which is of the EO sensor. Now that's a field pulse that we input into the TEM cell, 293 volts, 5 volts. Then DDOT measures pulse look like this, time derivative. But EO sensor earlier in the previous slide, it duplicates the field just exactly, but not now. When the DDOT sensor is close by, DDOT sensor distorts the field by itself. So EO sensor measures this distorted field, distorted by DDOTs. It also increases slightly and automatically. If you separate this EO and DDOT sensor a little further, let's say 5 to 6 centimeter from the DDOT sensor, it becomes a little better, but still, DDOT sensor still distorts the waveform. So that's the direct evidence that DDOT sensor or any sensor that contains metallic piece or semiconductor distort the field. And it doesn't measure true field at all. EO sensor, by the way, can measure correct waveform and the true field. Next, please.
One moment, it looks like we lost the slide. Here we go, slide 18.
So, okay, now, all right. Now, if you consider one single axis EO sensor, in the previous equation, we said the modulation depth is E field scalar product of Z directions. That means when E field is RF field is parallel to the probe beam directions, it measures the maximum output. It's depending on incoming direction phi, angle phi. If phi is 90 degree, that means incoming RF field is perpendicular to the probe beam direction. Then basically it doesn't measure any signals. There's a very strong directional dependence. So let's see how this equation works through experiment. We put sensor inside the TEM cell and we rotate it and change phi. If phi is 5 degree, or if it is 0, then you get 0 signal. If it is 5 degree, then you get very small signal. as phi becomes larger, close to 90 degree, we get larger and larger signals. So these are experimental dot, and the solid line is sine phi functions. So it follows the equation just exactly. And now the implication of that is, if you have a single axis sensor, EO sensor, you have to align this sensor to be parallel to the RF field, incoming RF field, which is not practical in most of the T&E experiment. Because even if you know incoming RF signal, the RF signal often scatters or reflected by other objectives and then change the direction of RF signal. So it's impossible to align that correctly. So to solve the problem, next please, next slide. We instead exploit that property using that the directional dependence, assemble 3 axes. Each single axis sensors are aligned x, y, and z directions. Then an incoming field in any direction with a phi and theta, then E field component x and y and z component of E field can be given these equations. From there, we can measure each x, y, z component of E field. Then calculate E total field, the field itself, using equation like this. Then also, since we know x, y, z component of E field, we can calculate the direction of E field. When we did the experiment, we see the directional measurement error is less than 1 degree. Please. Next slide, please. Next slide, please. Okay, so we tested that in experiment. We put EO sensor, 3-axis sensor inside the TEM cell, and we deliberately put the sensor slightly tilted. Theta is 73 degree, and phi is about 90 degree, just like that. And we applied 765 volt, and the distance between septum and the outer shell of a TEM was about 10.8 centimeter. So it produced about 7,083 volt per meter. Next, please. Next slide, please. So our data acquisition system, which we developed, can take X, Y, Z component of RF field and shows waveform and measure the E field strength, X component, Y component, Z component. Now X component is about 6,700 volt per meter. Y component is about 1,000 volt per meter. Z component is 2,000 volt per meter. From there, you add them up, you get about 7,078 volt per meter. Previous in the estimate from the potential of between the septum and outer shell of a TEM cell, we estimate E field is of 7,080 volt per meter, 7,080 volt. So it's very close to that number. And now from this XYZ component, using the equations shown here, you can extract incoming angle theta and phi, and that's a 73 degree and 8.8 degree, which is very highly consistent with what we already set up in the experiment. Next, please. Next slide, please. So it works. It detects E field or RF field, amplitude, waveform, and the direction. Now, by the way, the sensor crystals has a length L, which changes with if temperature changes. Also, optical component changes properties, physical properties slightly with temperature. So what we need in the before you use it for field test, we need to calibrate them. Calibrate them for each different frequencies and different temperatures. Next, please. So this is one of the examples that calibrated by NIST in 2010. That time we sent them our older prototype of EO sensor, and they measured that with TM cell from 1 megahertz to 500 megahertz at low frequencies. And if it is beyond about 7-8 volt per meter, it's just a straight, linear all the way. Below that, there is noise. But we solved this problem with the latest EO sensor. Next, please. Okay, that is performed by NIST for higher frequency, 750 megahertz to 10 gigahertz. So it's beyond that, about 3 volt per meter is all linear. But frequency dependence slope is slightly different because conversion factors are different. Next, please. So conversion factor that from the NIST data shown like this, at low frequencies, it's flat, then it drops down. That means sensitivity or responsivity of EO sensor improves at higher frequencies. That's old sensor. With the new sensor, we get that kind of slope. Of course, with the new one, we also have a higher responsivity, EO responsivity at higher frequencies. But look at these numbers. That's 2 million, and that's about 2 times 10 to the minus 4, 10 to the 4. That means about 2,000 times improvement of EO responsivity with our new sensors. We figured out how to improve the sensor, so we can further improve the EO sensitivity, and possibly in the coming next few years, we will be able to improve additional 2,000 times improvement. Next, please. So this is example of a field test with earlier EO sensor model prototypes. That time we have X, Y, Z EO sensor, and then there's one more MO sensor, magnetic optic field sensor. So you can measure electric field and magnetic field at the same time. And the sensor was about 20 meters away from the radar horn, and we detect that signal using 50-meter optical fibers goes into trailer. Then we can see the radar signal here in the spectrum analyzer. And it produces in the readout, it says this is earlier version of our data acquisition system, about 800 volt per meter, 61. So it's about less than 1,000 volt, 1 kilovolt per meter at a distance about 20 meters. Next, please. And we use the same EO sensor for A-band transmitter, and put EO sensor here and send the signal into it. Then it shows duty cycle here, pulse, 2 pulses. Then once we use different oscilloscope scale, we can see envelope. And when you expand it furthermore, the envelope, you can see inner RF signals. Next, please. Now this is interesting experiment carried out at NRL. We had a horn antenna, and we put pulsed signal shown here, apply the signal. Then sensor detects the signal directly, duplicate the pulse shape. And what we did, we put sensor very close to the horn antenna, right at the mouth of the horn antenna, and away from the horn antenna. measure that near field, then far field. At a certain distance, it follows one of R-type behavior. So we can measure both near field and far field. This is possible because EO sensor doesn't reflect back the RF signal back into the phone antenna. So it is safe to measure that RF field. When you do that right at the front of the RF phone antenna, you can mapping out the field distribution on the surface of that, which is typical text type of structures. So you can do that in any directions, any distances. Thank you. Next, please. Next slide, please. So specification of that EO sensor is ours can go from DC to about 20 gigahertz. We could go even further, but we haven't tried yet. I think the highest frequency we tried was 22 gigahertz. And for conventional sensors, it requires about 16 probes. For our EO sensor, we need only one that can cover entire frequency range. The size for the conventional one can be larger than 30 centimeter cube to smaller than 5 by 3 by 3 centimeter cube. In our case, it's all less than or smaller than, it's about 3 by 3 by 3 centimeter cube. It measures true field, whereas conventional one cannot measure the true field. And lowest field, minimum field, is about 100 millivolt, actually 0.1 volt per meter to about 1 volt, to maximum 500 kilovolt per meter. And we used optical fiber 50 meters. But once we tried 100 meter fiber, it worked fine too. Next, please. Next slide, please. So in summary, we developed a field deployable, non-intrusive E-field sensor that measures true E-field, and without perturbing the field that it measures. And the sensor's dynamic range is more than 5 order of magnitude, and the bandwidth is from sub-hertz or DC, zero frequency, to 20 gigahertz. And NRL EO sensor is ready for field test, even in very complex test environment. For the accurate field measurement, we need calibration of the sensor as a function of temperature as well as frequencies. For 3-axis sensor, we need additional calibration to verify the accuracy of measurement, field direction measurement. Other environmental effects such as the residual gas or humidity has not been tested, but we did some tests in very different environment, very humid summer and very dry winter, and contaminated the environment with a lot of noxious gas. We didn't see any any problem so far. So anecdotal evidence indicates that such environmental effect may not be significant with our EO sensor. That's it. Thank you for your attention. If you have a question, please ask me. Thank you.
Very good. Thank you, Dr. Wu. Appreciate that. We did have a few. If you will, let me go ahead and put them on the screen, and we can kind of discuss those in some time remaining. Might not get through them all, but I'm going to kind of file through them as they were submitted. So can you see this question as it appears on the screen, Dr. Wu?
Yeah, I see that question.
Okay. Do you have a reference or source for the fully magnetic
field sensor, but it is not field deployable yet. There's a few things, a few technical things we have to solve. In other words, is the magneto-optic materials that we use This we call bismuth doped garnet, and those crystals are available only in thick film form. That means we have to stack them together, and there is a magnetic domain issues. We have to align each one painstakingly by hand, and takes a lot of time. Also, material is not so cheap and it's expensive. So sensor is could be more than $2,000 or $3,000 for each. We have to solve that problem before you make it deployable. But if you are interested in this EP field sensor, we can make some prototypes. Sensitivity of B field sensor right this time, we could detect about 1 picotesla of B field at about a few hundred hertz. If it is say 1 hertz or sub-hertz, the sensitivity is about 10 picotesla range. At higher frequencies, of course, sensitivity is very high, less than 1 picotesla range. So it is available, but requires some kind of a research, little bit more research. If you have is that enough answer for you?
Well, he doesn't look like he'll be able to respond, but I think that's a sufficient answer. Yeah, I appreciate that.
So
let's jump to the next question. Yep.
Okay.
So same questioner, but how stable is the potassium deuterium phosphate crystal in the natural environment? Does this lead to problems in drift sensitivity or stability?
Yeah. So far, we haven't seen any problems. We haven't studied systematic. We haven't have not done any systematic study on environmental effect, but near NRL, some area is really contaminated. If you know about it, has a lot of toxic gas, and temperature is not right, very high, and humidity is sometimes over 90%, 95%. In my lab, sometimes reaches 98%. And the sensor was okay in that kind of environment. But to be sure, we have to do this environmental test more rigorously. And so so far, my question is, they are stable and sensitive.
Mm-hmm.
Yeah, thank you.
Very good, thank you. All right, next one here. Would you recommend using the sensor to help with quantifying the EM environment for laboratory and field testing of 5G communications and data transmittal equipment?
I say why not? I mean, it's possible, yes. In fact, occasionally out of curiosity, I put my cell phone right next to sensor and tested that. But if I put cell phone real far away, say a few 10 centimeters, it doesn't detect signal very well. So for 5G communication and data transmission equipment, we may need to improve sensitivity at least one order of magnitude, which could be done quite easily. But I didn't pay that much attention yet. But if you are interested in, we will do so. We will develop it more sensitive.
Yes.
Okay.
Let me jump to this kind of follow-up question that was just submitted related to that. To say one of the issues is that the sensor that you've described has been tested up to 20 gigahertz, but the 5G frequency spectrum will be in the sub-6.
Yeah.
So I think it's just kind of acknowledging what you just mentioned.
Yes. Okay. Yeah, up to 6 gigahertz is fine. We in my lab we have a terahertz facilities too, and in one of terahertz facilities goes to about 5 terahertz, from starting about 70 or 50 gigahertz to 5 terahertz. We use electro-optic sensor for that sensing. So high frequency is possible, but we need to invest at least a couple of years or 3 years of investment on the sensor, high frequency sensors, especially going to millimeter wave. And the millimeter wave is directional, and some of the millimeter wave sources are not very strong, may produce about milliwatt or smaller. So we need to increase sensitivity and to detect the high frequencies. But as you see, I don't know if you catch it, higher frequency capability means less EO responsivity. So we have to somehow develop a new trick to make it more sensitive at higher frequencies. Okay?
Yep, very good. Let me put this question up here. Looks like most of the data presented is in the megahertz to gigahertz range. How does the sensor perform in the 20 kilohertz?
Yeah, we have some data, but I didn't include it. If you want, contact me by email. I'll show you low frequency data, even far below kilohertz. So we have some data, sub-hertz to about 1 megahertz range. So we may need to see more carefully with the 20 kilohertz to 750 kilohertz. It can be done quite quickly in our lab. So we can take data and provide you.
Okay, let me pull this question up. Accidentally skipped past a moment ago. How did you go from the Pockels effect EO formulas to get the NRL EO sensor equation that you can recommend for deeper understanding of the Pockels effect? Not enough to maybe rattle off here, but
I don't know. The equation all that's shown is mostly derived by myself, and some effort with my group member. So it's just a pure mathematics. If you want, the derivation is about, if I remember right, 5 to 10 pages altogether. If you want it, then I can provide you the derivation. I don't take this equation from some other reference papers.
Okay, so and like you just mentioned in the previous question too, you're open to respond to someone to reach out to you via email.
Yeah, sure, I'll do.
Very good. Okay.
Of course.
The developed EO data acquisition software.
Yeah, of course. Okay. We constantly improving it, and software is the nature of software is improvement every time. But as is, if you want it, we can provide the software.
And would you be a?
Yeah, we will be able to do it. Just let me know. Well, first, I'll ask NR security department, see if it is okay. Once they say okay, we can do it. Okay, not a problem at all.
Very good, perfect. All right, and then last question here. What is the operating temperature range? Does the temperature need to be fixed? Does the frequency being measured need to be known for accurate measurements?
Yeah, okay, that's a good question. Very good question. Operating temperature, we earlier when we do field test, we did it in very cold temperature, like below 0 Fahrenheit degree to about 180 degree, and that is right over the testing site. There is a ground plate with a mild steel laying on, so sun reflected from the ground plane, and it made it really hot, 180 degrees, something like that. And sensor worked fine within that temperature range. But to be more specific about your question, we are carrying out temperature dependence tests inside the temperature cell. That goes temperature minus 20 Celsius degree to about 80 Celsius degree. So I think in usual temperature testing site in any other place in on Earth, mostly within the range of minus 20 Celsius degree to plus 80 Celsius degree, unless you go Antarctica or some other places. Okay, is that answer?
Very good. Yep. I think so, yes. That's very adequate. Thank you so much. All right. Well, the last question here, we've certainly gone over time a bit, but I appreciate you sticking with us, Dr. Wu, and the presentation. Great job. If anyone does have any other follow-up questions, like you mentioned, you're open to receive some emails and field questions that way. People can also reach out to DSIAC, and we'd be able to help out facilitated answers as well.
Sure.
Thank you very much for your time.
Thank you for your attention, and thank you for the opportunity to present it. Thank you so much.
Absolutely.